Kimi K3 has 2.8 trillion parameters. That sentence sounds like the whole explanation. Bigger number, bigger brain, better model. But that interpretation is wrong in 3 different ways. First, total parameters are not the same as active parameters. Second, stored model size is not the same as compute used for one token. And third, parameter count alone does not tell you whether a model is useful. So let us open the box. A parameter is a learned numerical value inside a neural network. During training, the model adjusts enormous collections of these values so that its predictions become more useful. In a dense model, most of the network participates whenever the model processes a token. If you double the number of parameters, you generally increase both the capacity and the amount of work required. Kimi K3 is different. It uses mixture of experts. Inside K3 are 896 routed experts. For each token, a router chooses 16. Imagine a building containing 896 specialist rooms. One room may be useful for code structure, another for mathematical patterns, another for visual relationships, and many will contain overlapping skills. When a token arrives, the router does not switch on the entire building. It sends that token to a small selection of rooms. The whole building still has to exist. The weights still have to be stored somewhere, but only a small root performs the expert computation for that token. This is the first distinction: storage scale versus active computation. 2.8 trillion describes the total learned capacity. 16 out of 896 describes the routing sparsity. Moonshot has not yet published a simple official active parameter number for K3 in the launch material. So if someone confidently tells you that K3 activates exactly this many billions of parameters per token, ask for the technical report. At the time of this script, that report has not been released. Mixture of experts creates an attractive bargain, but it also creates hard engineering problems. The router must send tokens to useful experts. If it repeatedly chooses the wrong specialists, the giant model wastes its capacity. The training system must keep experts balanced. If a few experts receive most of the traffic while others remain idle, some accelerators become overloaded and others wait. The serving system must move expert weights and intermediate results across many devices quickly enough that communication does not erase the compute savings. At K3 scale, routing is not a detail. Routing is part of the model's intelligence and part of the infrastructure bill. Moonshot says it uses a stable latent MOE framework, a balancing method based on router score quantiles, and a fully balanced expert parallel training design. The goal is to keep the sparse network stable while spreading work efficiently across hardware. Then the model adds quantization-aware training. Moonshot says K3 uses MXFP4 weights and MXFP8 activations from the supervised fine-tuning stage onward. In simple language, the stored weights use a compact, low-precision representation, while active calculations use a somewhat wider format. Why does that matter? Because 2.8 trillion ordinary 16-bit weights would require roughly 5.6 terabytes before counting overhead. At 4 bits per weight, the mathematical floor falls to around 1.4 terabytes. That is an enormous reduction. It is also still enormous. Quantization makes K3 more deployable. It does not transform it into a laptop model. Moonshot recommends supernode configurations containing at least 64 accelerators for deployment. That single recommendation tells you more about the practical scale than the word open ever could. Now we can address the biggest misconception. Does 2.8 trillion parameters mean Kimi K3 is automatically smarter than GPT 5.6 Sol or Claude Fable 5? No, parameter count tells us something about model capacity and architecture. It does not tell us how good the training data was, how effectively the experts specialize, whether the router selects them correctly, how strong post-training was, how reliable the agent harness is, or how well the model behaves on your task. Moonshot itself says K3 still trails the strongest proprietary models in overall user experience. This is why comparing model sizes across architectures can become misleading. A dense model and a sparse model do not spend compute in the same way. 2 sparse models with the same total size may activate different fractions. A smaller model with better training may outperform a larger model. A huge context window may help one workflow and add noise to another. The useful way to read Kimi K3's number is this. 2.8 trillion parameters means Moonshot has built an extraordinarily large reservoir of learned weights. 16 selected experts means the model attempts to access that reservoir sparsely. Low-precision weights reduce the memory burden. Kimi delta attention and attention residuals attempt to make information flow efficiently across context and depth, and a large distributed serving system keeps the entire machine moving. That is the real K3 story, not one giant brain waking up for every word. A massive library, a selective router, a small active team, and an industrial-scale machine keeping the doors open. The 2.8 trillion number is real, but without the architecture underneath it, that number explains almost nothing.